Hey everyone, here in my office, and I want to talk a little bit more about intermolecular forces or attractive forces between molecules, and specifically how it relates to solubility, whether something will dissolve. Chemists have a really simple rule of thumb for this. We say like dissolves like. Basically, similar things with similar intermolecular forces will mix together, essentially. That means polar molecules will like to mix with other polar molecules, and nonpolar molecules will like to mix with other nonpolar molecules. So let's see how this works. I have a little example here with vegetable oil and water, and we want to see what happens when they mix. And just to give you an idea on the molecular level what we're talking about here, water molecules are like this. They're polar and hydrogen bonding, so the special kind of polarity that we call hydrogen bonding. So they have very strong attractions to each other. And these are nonpolar molecules to represent oil. So oil is a nonpolar molecule that's essentially just a bunch of these units repeated over and over and over again. So when we mix the two, what will happen? We'll pour the two together into this container, and after the initial mixing, you start to see that they do not like each other at all. The oil starts separating out and rising to the top, and the water to the bottom. So what we're saying here is that the oil molecules end up mixing with other oil molecules because the water molecules have a strong attraction to themselves. So they stick to each other first. So even if they started out mixed, this water molecule is going to have a strong attraction to that water molecule. So it's going to bump them out of the way, stick to other water molecules, and over time that will make the two separate out from each other, and that's what you get here. And it'll take a little while. You know, we mix them together, so they'll form a little bit of, we call that an emulsion layer, but over time they'll separate out more and more. And you've seen this with oil and vinegar salad dressing or lots of different things. So to drive this point home, we want to take this one step further and give you an even more, another demonstration that illustrates the point even more. So for this, for water, we're going to represent with these little magnets. We call these stir bars. We use them in chemistry lab for some different tasks. And for oil, we're going to represent that with these just glass marbles. So let's see what happens when we mix the two together. So these are just magnets. So they, by themselves, they just sit like that. But if you stick others together, they will eventually attract each other. So we're going to throw a few of these magnets in the bottom. And then we're going to throw some marbles over there. And then we're going to throw in a few more of these. And these magnets are representing the water molecules, and these marbles, glass marbles that aren't attracted to each other, are representing the oil molecules, the nonpolar molecules. So we'll throw some more in. We'll just scatter them out. Notice they're not stuck to each other right now. And then we'll pour in marbles, and then some more water molecules. Spread around. And then that's the last of our marbles, and we'll throw in a couple more water molecules on top for good measure. Now you can clearly see that the magnets are spread out evenly throughout. They're not all in one place, they're spread out even, but what do you think is going to happen if we start shaking this around now and giving them time to move around? Well, you can already see it happening. They start to clump together because those magnets are attracted to each other, just like water molecules are attracted to other water molecules. They're not attracted to the glass marbles, just like these are not attracted to the nonpolar molecules here. So we can just keep shaking this around, keep rolling it around, keep rolling it around. And the more that happens, the more opportunity those magnets have to bump into each other. They will stick together and form one layer. big clump of water molecules, one area separated out from the clump of the nonpolar molecules. And that is the basic theory of why like dissolves like. Why polar things mix with other polar things and nonpolar things mix with other nonpolar things. So I like to always finish this with a question, or in this case I like to finish it with a question. So how would we answer this if we were asked a question about this on your exam? This is the same idea here. We've got this question. It says, pick the compound in each pair, so there's a pair of molecules here and a pair here and a pair here, that would have the higher solubility in water. So we're looking for the one that's more similar to a water molecule. So to think about this, remember water molecule is polar and hydrogen bonding. So it has the dipole-dipole forces and the hydrogen bonding. So the best molecule would be, ideally, would be able to do the hydrogen bonding. And if it couldn't do hydrogen bonding, then it would at least need to be polar so that it could do the dipole-dipole attractions with water. So 1, we're looking for things that can do hydrogen bonding. 2, we're looking for things that can be polar and have dipole-dipole attractive forces. So if we're looking at this first one, there's nothing here able to do hydrogen bonding. This molecule here, I don't know if you can tell by this picture, but this molecule here has carbons in a chain bonded to oxygen, and then other carbons, and then other carbons. And the hydrogens are all coming off of the carbons like that. So it will be polar around the oxygen, and this one will be totally nonpolar because it's just carbon and hydrogen. So in this case, it would be this molecule in the pair that would be better. That would be polar, so it would mix better with water than this one that's nonpolar. In this case, here we spot something interesting. This one has a hydrogen directly bonded to a nitrogen. So that molecule is polar with hydrogen bonding. So that definitely is going to bond better in water than this nonpolar molecule. And now down here, we have something even more interesting. In this last one, we have an OH, so that can do hydrogen bonding, and an OH, so that can also do hydrogen bonding. How will we decide which one is better? Well, in this case, the OH is with 2 carbons of nonpolar, or a nonpolar section of the molecule. And in this case, the OH is with 1, 2, 3, 4, 5 carbons that would all be on their own nonpolar, except for their attachment to oxygen. So in this case, the one that's more like water is the one that's small with more of the polar hydrogen bonding parts by a percentage of the molecule. So there you go. Out of these two, a polar molecule is better than a nonpolar at dissolving in water. A polar with hydrogen is better than a nonpolar. With hydrogen bonding is better than a nonpolar. And between two things that are hydrogen bonding, you're looking for one that a higher percentage of the molecule is like the one that it's going to dissolve in. And that's it. That's been your discussion of solubility.